Hello, my name is Jeremy Seek, and I'm a professor at Indiana University. And today's video is going to be continuing our series about the Deduce proof assistant. And we'll be talking about how to do equational reasoning about numbers in arithmetic. Okay, so we're just going to work through one sort of example here. Of doing some algebra, and so here we go. We're going to prove that a simple equation here. We're going to have some 1 plus x quantity times 2 plus x, right? And then what polynomial is that equivalent to? That's x squared plus 3x plus 2. Okay, and we're going to show how to prove this theorem in Deduce, and we're going to be using some basic equations that are in the Deduce standard library. You can see I've imported the unsigned integer library, and over here I've got open that library and all the theorems that are in it. For example, you can see that here we have the theorem that says that multiplication distributes over addition. This one's for on the left, and then here if you have multiplication on the right, that also distributes over addition. So we'll be using some of those theorems. Let's see, there's a couple other ones too, like add, commute. Okay, if you have x plus y, that's equal to y plus x. So we'll be using those theorems from the library. Okay, so all right, we need to prove an all statement here. So we'll let Deduce remind us what we should do here. Of course, that means we need to say, okay, let x be an arbitrary integer, and let's then try to proceed with the proof with that sort of arbitrarily chosen integer. Sort of a placeholder for any integer. Okay, so now we have this equation to prove. And so here I want to introduce a new feature of Deduce. It's called equations. So this is a new keyword. And this feature is going to come in handy when you have an equation that you want to prove that's going to use lots of steps in the proof. Okay, so maybe you're used to writing on paper, something equals something equals something equals something equals something, a whole bunch of steps of equations with the different reasons for them. This equations feature is going to let us do the same thing. Okay, so typically what I like to do is go ahead and just sort of copy and paste our goal in there. Okay. And right, we could say by sorry here to get started, and Deduce is going to be like, okay, great, that all parses and checks out, except that we now need to fill in this sorry. Okay, so we're going to try to do this step by step. Okay, so that'll be our last step will be that, but let's see what our first step is. Well, maybe let's sort of use one of these distributivity laws. We've got this quantity over here multiplied by, an addition, right? So if we look down over here, if we look at this theorem here, we've got a multiplication and then addition. So we could go ahead and apply that. And what's that going to look like? Well, we're going to have 1 plus x times 2. And then 1 plus x times x. Okay, so we want to use this equation, the distributive multiplicity. And so the way we use an equation to change our goal is using the replace keyword. Okay, so that should get us from here to then having the multiplication distributed. Okay, the multiplication by 1 plus x. Okay, now one thing to notice here is I've used this dot, dot, dot. Okay, and the 3 dots, the ellipses, is basically a placeholder for whatever was the right-hand side of the equation one line above. Okay, so this dot, dot, dot here is just shorthand for this equation here. Okay, so like the overall proof is going to be like, okay, this is equal to this, and that is going to be equal to the final step, you know, and we'll have to fill that in. Okay, so let's go ahead and ask Deduce to check this. It was happy with this first step, and then now it's just saying that the rest is unfinished. Okay, so now we can keep going like this. Okay, so now we've got a multiplication on the right of an addition and another multiplication on the right of an addition. Okay, so now we're going to be able to use this other distributivity law, okay, down here. We've got multiplication on the right. So 2 times 1, that's going to be 2. I have x times 2 there. Okay, great. And then over here, we're going to have x plus x squared. Right now, we're using the distribution of multiplication on the right. All right, so far so good. Okay, now the next thing we want to do here is now we've got this x times 2 and x. You know, those are both, those are both, in x, and we want to get that to being, a 3x, right? Okay, so we can do that with yet another sort of distributivity. So this is going to be like x times 2 plus 1, right? This is going to be equivalent to that. Okay, and then we still have x squared there. Now, one thing that's a little bit different about the next step here is that here we want to, in some sense, we want to work backwards. We want to transform this formula into this formula by using distributivity. Okay, so we're sort of working backwards, and to tell Deduce that we want to apply this equation coming up, right? We're going to be applying, we're going to be doing this distributivity, but we want to apply it to the right-hand side of the equation, whereas what we've been doing so far is applying it to the left-hand side, sort of working forward. Here we're working backwards. So we're going to put these hash marks around the part of the equation that we want to apply this equation to. Okay, so we'll go ahead and do that. It wasn't quite happy about that. It's sometimes Deduce has trouble inferring the variables that we pick for our equation. Okay, so for example, here we need to pick an a and an x and a y. So here the a in the equation corresponds to the x in the up here in the theorem that we're trying to prove, and then the x and the y in the equation down here correspond to 2 and 1. Okay, so then Deduce was happy. Okay, so we had to sort of hold its hand a little bit to say what values to use for those variables in the equation. Okay, so far so good. All right, so now maybe just our next step, maybe we just turn this into a 3 here. Right, Deduce can do that automatically. We don't even have to tell it how to do that. Okay. And then let's look at where we're headed here. Okay, now we basically just need to reorganize some things a little bit. Okay, so we need to like move this to towards the back, right? So we can use commutativity of addition to start reordering these things. All right, so I'm just going to reorder those. That'll be by the commutativity of addition. Let's see if Deduce likes that. Yep, that's so far so good. And then now, kind of looking where we're going here, the last thing we need to do is, well, the second to last thing, we want to move that to the front. Okay, so we'll have x squared plus x times 3 plus 2. So we'll do another, this will be another commutativity. But this time what we're swapping is the x times 3 plus 2 and the x squared. All right, and then for the very final step here, we just need to flip the x times 3 to be 3 times x. So that's the commutativity of multiplication this time, right? Commute x and 3. Great. So that completes our proof of this little piece of algebra. Okay, so I think we'll stop there for this video, and then next time we'll get into some other proof techniques, such as being able to sort of switch on a union data type, and then also being able to do replace and expand, but applying it to a premise instead of applying it to the current goal. I'll see you next time.